I must excuse myself. I changed the title and the subject of my talk because in the meanwhile, with Emilio Turco and Emilio Barchesi, we started getting very interesting results. So in case we had no time to discuss all details all together, in case I will ask them to give you some extra details in the spirit of informal discussion we have here, Emilio Barchesi will be obliged to give a talk Friday or Tuesday. Friday. Okay. So let us start. Somebody, someone in particular, remarked that my complex glasses are not anymore needed. I want to tell you this. The power of 3D printing. My cornea has a very crazy shape, so some optician made a topography of my cornea, could find the field of which is the defect when you have cylindrical lenses, astigmatism, the field of astigmatic direction in my eye, and they printed a multifocal, multi-axis lens. And this is a good introduction to what I will try to tell you now. 3D printing is opening unbelievable possibilities of applications. In particular, and so I can start now, but I prefer to sit to avoid always troubles. In particular, we have the possibility to do experiments in a situation where before it was not possible to do anything. These are not the authors of the original results I will try to present you here. These are simply those Emilio Turco and Emilio Barchesi who helped me in preparing this slide and with whom I'm working in this period on a daily basis. I will tell you that, for instance, this reasoning, I will try to describe you quickly, has been developed on the blackboard of Pierre Sepecher office some 2 years ago, for instance, probably. So the idea is, many years ago, around year 2000, I published some papers about second gradient continua. Now, maybe everybody knows about it, but let us tell slowly that in general, you can have a continuum whose deformation energy depends not only on the first gradient of placement, but also on the second gradient of placement. For some historical, I would say rather sociological reasons, these continua are not appreciated by a group of mechanicians. Let us say something like that. So in those years with Pierre, we had the idea to try to synthesize a microstructure whose homogenized counterpart was a second gradient continuum. Okay? This is not a new problem in science. Maybe somebody among you will remember that there was a time when analog computers were invented, and analog computers were doing what? Given an equation, I find you an electric circuit whose governing equations are the starting equations. This is a very similar problem. We have a deformation energy, and we ask ourselves, which is the microstructure which once homogenized gives us the energy we have chosen a priori. So this is something very, very similar as a spirit. Okay. Now, to tell you how old is this paper, we exchanged with Pierre some fax. We have sent each other faxes. This is prehistory. It is interesting to tell you that these were dreams. They were pure conceptual constructions. We waited 15 years and we have printed this with a 3D printer. So the possibility, what is happening is the scale of time is changed dramatically. Okay? So, which was our problem? Our problem was to find a material whose deformation energy depends only on second gradient of displacement, so-called a pure metamaterial, pure second gradient metamaterial. Okay, now the trick was the following. Look at this pantographic structure. I call it pantographic, you can call it with another name. I call it pantographic because on the trains you have the pantograph, which is based on this principle. Look at this picture. If you change this angle here, you have no change in the energy. Actually, in the deformation energy. Actually, what we have is speaking French, so you understand. Mécanique des machines, meccanica delle macchine. So you have a set of rigid bodies with perfect constraints, with some residual degrees of freedom. Okay? Now, in the integration scheme which we have now, we represented the beams which constitute this cross with one elongation spring here, another elongation spring here, and a bending spring in the center, using what is called usually a Henke type model for discrete model for a beam. Okay? In the case of inextensible bars, it has been proven that this scheme converges to, gamma converges to the problem of homogenized systems with beams. Okay? So, we decided to use this simplified energy in order to have a simpler way for attacking numerical simulations, those numerical simulations which I will show you. Emilio Barchiesi will tell you all details of the deduction. It is out of focus. The deduction which we tried to do. No. So the slide is not of good quality. The deduction which we have tried to do for getting an homogenized beam equation in nonlinear configurations for this. The big problem is that the homogenization procedure assumes that this angle is always between 0 and pi. Okay? So we could get an homogenized version of this discrete system under some assumptions. Okay? And we checked then numerically, I will tell you that this homogenization gives interesting results.
But which are the features of the continua you obtain by homogenization?
I will give you, okay, this,
second gradient, isotropic elasticity.
no, this is a beam, this is a beam. This is, once homogenized, the red line becomes a one-dimensional continuum.
Yes.
So we have an energy in which you have not only the second derivative of transverse displacement, which is standard beam theory, but you have also the second derivative of axial displacement in the deformation energy. Okay? And gamma convergence of this has been proven in the case of linearized equations in the neighborhood of the reference configuration. Okay? And what we got, and this will be the job of Emilio Barchesi, we got the energy for homogenization of this beam under of this structure under the assumption that this angle remains always between 0 and pi. Okay? So it cannot become negative. So you cannot get the flip-flop behavior. I will tell you with some pictures. Okay, so now the question is, we have this object, and we know that this object is rather interesting. By the way, if you try to study existence and uniqueness of linearized equations for this object and some related objects, you find very difficult problems, but let's go ahead. Now, I will tell you later. Okay, so we started for proving that second gradient materials are of relevance. They are describing something. But at the end of my presentation, I will tell you that maybe even continuum theories are totally useless. But I leave to you this discussion. Okay, now the idea is this one. You have this microstructure. This is a deformation with zero energy. So in order to have a deformation energy for this beam, you need that every pair of these blue points have a different distance. Because if these 2 points have a different distance with respect to these other 2 points, then the beams are deformed, and so you have an energy. Emilio Barchesi will tell you that this is the energy for the homogenized beam, where rho is the elongation of the beam, and theta prime is the bending of the beam. So what you can say is that linearizing this energy, you get, if u is the displacement in the axial direction, u is exactly the elongation. Okay. Now you can build pantographic beams in the x direction, pantographic beams on the y direction, and you can try to see what happens once you homogenize this structure. Okay, you make simple calculations, and what you discover that in plane displacement, u1, u2 appear in the deformation energy with the second derivative. So if you think about standard plate theory, the in-plane displacement is not producing, the second derivatives are not producing any energy. So this animal, if the pivots are perfect, so no deformation energy in every pivot, the linearized energy, here it is. So you have du second over dx2 square in the energy, for instance. So you have some energy which are not studied in other situations. Now, the fiber of this bipantographic fabric are pantographs themselves. Okay? So if you remember, I was studying in the last years this kind of structure where in every crossing point you have a perfect pivot, okay? Now you have a two-scale microstructure. You have one scale at the level of this pantograph, okay? And one scale with an assembly of pantographs. Okay, so you have the length scale of the beam constituting each pantograph. Then you have the length scale of the distance between two pivots in each pantograph. And then you have the length scale of the distance between two pantographic beams. And these three scales can be separated in our design. Now we cut this. We cut this part of the pantograph and mirror. We can print. We can print this. 3D printing. Look, let me spend a few words telling you that notwithstanding what is said by British people, European Union is very good. This 3D printing has been made possible by European Union giving 1.5 million euros to Warsaw University of Technology. There, 3 scientists spend something like 2 years of their life for getting the best performances out of this 3D printer, and we are capable to print a perfect pivot with a space between the inner part and the outer part. And this space is 0.2 millimeters. I want to pull the leg a little bit of every French being here. I tried to get this quality 3D printing by many French groups, and up to now, I did not manage. Okay, we don't talk about Italy, of course. Okay, but you should be very upset and ask your colleagues doing 3D printing to contact me as quickly as possible, because you cannot accept that France cannot have this technological possibility. You know, la grandeur de la France est terminée alors. Okay?
I thought you made one at Arpino, there was one.
They never managed to do any perfect pivot.
It's metallic or
Metallic. And okay, I will tell you about metallic and polymers. Okay, anyway, I am ready to discuss about it. Consider that, okay, I don't know why the resolution of this slide is so bad. Here you have a unique cylinder. So you have some deformation energy in the twist, while here in the red, you have the standard design of a perfect pivot. You need a run-in system, so a rodage, c'est nécessaire un rodage, because you must clean the space between the pivots in order to get some nice experiments.
Which metallic material?
No, this is polymer for the moment. Okay. Now, you can see the several scales. This is a microscope picture of the 3D printed polymer. The granular nature of this is clear. Then you have different length scales, and you can model this as a continuum, or you can model this as a set of springs with a kind of meso model. Okay? Very well. So here you have many different scales, but here everybody is aware of all this. Now, I must thank somebody in this room, okay, who invited me to give a talk in Cachan. And thanks to that talk, I met François Hild. François Hild is the genius of digital image correlation. But, you know, let me say something, not only about Francois, about the French school. Only in France you find experimental people who know about variational principles and can talk about Sobolev spaces. Okay? So with Francois, we had very nice discussion about what we were doing. This is not the movie, Emilio? The next. Okay? So, okay. Now, the peculiarity of this material, you remember we start from 200. Okay? And you remain in the elastic regime until 280, Emilio?
87 millimeters of displacement.
Yeah. And you can go, of course, this is a polymer, but we believe that this behavior is fundamentally elastic. Okay. The analysis of this phenomenon, okay, Pierre sent this paper in a journal published in India. They are very happy of this because this paper has been cited several times. We conceived this system purely on theoretical basis. Okay? And this is a material having very large elongation remaining in an elastic regime. With the long arm pantograph, so with beams which are not pantographic beams constituting the fabric, you get 40 millimeters of elongation. Here you manage to get 80, but I think we can optimize. I don't see here Boris Demora. Boris Demora is another very clever French scientist with a small defect, so I leave it on video recorded in YouTube. He is a perfectionist. So we have an optimization result about these structures, which we don't publish because Boris must complete writing the perfect paper. Okay? But I will oblige him to do this publication. Okay? So this is a very important result, I think. Now, look the beautiful pictures of Francois Hild. So, he uses this technicality. I must tell you what is very clever, I think, in Francois' approach. He uses meshes for elaborating the image. So the same this is very efficient from conceptual point of view. You take one mesh, okay? You design the specimen. Then you use it with COMSOL and you get a numerical simulation. You send the same file to the 3D printer and you get the physical object. You give this mesh to Francois Hild and he gets the image correlation, digital image correlation. Okay, now there are some technicalities. Maybe Emilio Barchesi will tell you some of them. This is using a system in which this mesh is not taking into account in the right way the empty spaces in this device. But look how beautifully this gives you the concentration of deformation. These are the linear measures of deformation. Okay, so we know exactly where the biggest deformation is taking place so that we can forecast. This will be the presentation of Mario Spagnuolo in one of the next days, because Mario Spagnuolo, he works with Francois Hild also, looking at this pattern can tell you where this specimen will be broken. inventing a criterion of damage based on deformation. Okay. Okay. Here is the refined digital image correlation where the empty space is considered in the algorithm. Okay. Now, consider that I, another time, like very much collaboration. I tell you why. In Warsaw, they can print very well. They have very good machines, but very bad cameras. Okay? So we do the testing, and the pictures are not as good as they should be. Finally, they could buy good cameras at the end of the story. However, they don't have the know-how for doing digital image correlation in an efficient way. So for getting this result in Warsaw, you need 2 months. While Francois can do it in few days. So the Erasmus idea that science is obtained traveling a lot, I think it is a very good one. You must take the best from everywhere to get a joint result. Okay. By the way, these measures are made in Berlin, if I remember well, in the lab of Wolfgang Müller. Okay, so in this project there are many different people involved. Okay. I want to tell you here that you can shear this specimen, and this shear can cause out-of-plane buckling. And we are at the very beginning of these investigations. This is a first picture in which you get the measurements of out-of-plane buckling, okay, for these specimens.
So the cycle is open.
This cycle is the rodage, the run-in. All these, these small cycles here.
Energy or what?
This is displacement, this is force. Okay, so we start with many run-ins. Okay, when it is clean, we arrive at the rupture. We have some ruptures, and then we go back. By the way, there is a problem here. The displacement is so big that we have troubles. There are no machines which can measure such kind of deformations. So we must invent some experimental device for being able to handle these elastic deformations.
So before failure, you are purely elastic.
We are elastic until here, more or less.
Okay,
But
that's
there-
clear.
But there is, in the cycles we see, there is a small surface in the cycle.
These small circles are the rodage, run-in. As I told you, when you print these, you have some grains inside the perfect pivot. You must get rid of this.
So it's a kind of friction that we see.
This is a kind of energy needed for getting rid of the powder which remained in the perfect pivots.
You have some area inside this.
And this is, I don't know if this friction or the energy needed for breaking the grains and getting rid of them. Okay? I mean, I think I must give, let us give credits. We say that you must give to Caesar what is owed to Caesar. I don't know how to say it in English. It is a biblical statement. Okay? This idea for doing perfect pivots is due to a student, somebody with a master's degree, Maciej Golasewski, if I pronounce, from Warsaw University of Technology. He dared to print this specimen in this way. And when they told him, but there are some grains, he said, okay, I will do running and I will get rid of these grains. So this is the main trick which allows us to have large displacements. Okay? Okay, now what we want to do. We want to do a 3-point bending test. Okay, so what we do? We block here the final pivot. We allow this roller to be acted so you can have only horizontal displacement, and we impose this displacement in the middle of this. I repeat, because Pierre was asking me 2 times, we assure you, otherwise we kill Emilio Turco, that we are not doing this for half the specimen, we do it for the whole specimen. So symmetry is a result, not an assumption. Okay? And we model with Encke type models this structure. So between here and here you have an extensional spring, you have a rotational spring which models bending, and you have the other one which is an extensional spring. Okay? So this is the numerical code which we are doing. Now, before going to tell you in details everything about numerical evidence which we have, I tell you what this very nice propaganda, this is a very nice propaganda plot. What we have? We have here the central displacement in the abscissa, the resultant force in the ordinate. And we have a peculiar behavior. So let us tell what happens. Here you have a standard nonlinear deformation with both bending and extension. Then you reach a maximum, then you have a softening. Okay? Why? Because you are activating enough pantographic deformations which have a very low energy. Then something happens here. What it happens? Here these bars are straight, and then here the angle is not anymore between 0 and pi, it goes to the negative value. And you have this small jump here. Okay?
Just another question. We have to discuss.
Please.
Your test is displacement control.
Yes.
What will happen if you are force control?
I don't know if we have pictures. If we did both. By the way,
Yeah.
Emilio Turco, I don't know why, he prefers force-controlled tests, which are very difficult to interpret. And we started with force control, and we decided that it is much better to do force control. By the way, we got the same results, are exactly the same.
If you are force control, you cannot pass the peak of force.
The same plot by in this plot L is the displacement, and in the ordinate is the reaction corresponding to the displacement. If you change and use the force, you measure the corresponding displacement. This is
but the code of Emilio is capable to go beyond this. I will tell you.
Because you have displacement.
No, also if you have forces.
Because use a risk strategy.
I will tell you, Felix, I have a slide for this. I will tell you this. Okay, but I wanted to tell you some about the results. Okay, and then what is what is very nice is that you get a stiffening of this. So when you go beyond this threshold, you have a stiffening. So if I remember well, but Emilio Barchesi will tell you the details, continuum models doesn't manage to go beyond that point, right? Okay. So let's go now.
And the small jump that we see there,
Yes.
small jump, it is a numerical artifact or it is
No,
a
no.
solution there that the system jumps to?
You have a beam which is made like that. Okay? It is deformed like this, then it goes back and it deforms like that. In the very moment when the central beams, it is like von Mises beam.
I understand that physics is just that when I solve my equations, if I have this jump, that means that I jump to one of the two solutions or many that the system might have abruptly. But if I do an arc length, I would
It
be
is
able-
made with an arc
Yeah.
length.
I would be able to continue without having this jump, at least in principle. That means that I have at least two solutions there.
Kind of snapback.
No, it is a snap.
I think vedi se riesci a fargli vedere l'immagine prima e l'immagine dopo.
Okay, look, maybe we go to the presentation because we have some zoom on this, okay? So, this is the 3-point bending test, okay? And here you have the bars which are more or less straight, and then they change the angle, okay? Maybe I have a picture. Okay, here, okay, we'll go back to that. This is, here before the jump, you have these straight lines, and after the jump, the angle has changed the sign. So probably it is the discrete step. You should zoom in a better way to get a better definition of this.
Is it a bifurcation point there or it is something else? Physically understand it, that this jump.
No, I don't think it is a bifurcation. It is a local snap through.
It's the same mechanism of the von Mises arch. Von Mises arch has two beams in this position, and when the load is imposed, the arch go in this situation, and after this there is a line. This is exactly the same,
Yeah, but-
only it's for two.
But the bifurcation diagram is continuing, even in the von Mises.
I don't know if in this case there is a bifurcation point. I have no.
Okay, but the stiffness matrix is always definite positive.
In this case, yes. There are some.
If you want bifurcation, you must wait some slides. They will arrive. Okay? But I don't think, look, these are numerical simulations. I don't have any answer to tell you, but numerically, the second derivatives matrix is definite positive all the time along this.
But you mentioned the arc length technique. What kind of arc are you considering to have this?
We go where it is. You send me the picture, Emilio. No. There is one page of Rick's.
Sulle altre che ti ho mandato.
Ah, so I am wrong. Sorry, I did not use the.
But the peculiarities of this term is the constraint is only the orthogonality between the extrapolation and the correction.
E questa?
No constraints on the arc length. There is only the constraint between the extrapolation, which is obtained using Newton's standard Newton method, and the correction, which is a kind of linearization of the extrapolation. Very, very simple to do. Okay, questa.
Eccola qua. Sorry, I was using an old version of the presentation. So as everybody is asking about this, we try to tell you what we did. So the
Just the important is the constraint of the arc that you what.
You mean the constraint?
Yeah, the constraint that you have in your arc length method.
Yes. So you have.
Can I write something?
Yes. Cardillo, where are you going?
Okay, this is an equilibrium point, and this is the previous equilibrium point. There is an extrapolation between these 2 points to have an extrapolation point. The correction is simply obtained using the orthogonality between this extrapolation until we reach the point. Only this.
The question
is much more simple than the original implementation of Arpino.
the question is if it is two solutions, or if it is maybe it does something like this, there, like this, and actually, if you have a big step in your arc length, you may jump directly here and lose this branch. Okay. Or if it may be another, it may be a bifurcation.
You are impatient. we believe that we have found this later.
Okay.
Okay, but we are aware of this, but I don't believe that in this small jump this is hidden. Okay, but we could be.
The length of the is a variable depending from the number of iterations of the previous steps. In this way, we have a small step when we are in this part of the curve.
Okay.
It's an adaptive method.
Okay, now to answer to Felix. If you take a given resultant, you get 3 different forces, 3 different displacements. Okay? And the shape is this one for the smallest displacement. This one for the second bigger, this one. And then here, after the stiffening, you have this one. So you have 3 different mechanisms, and here you have the deformation energy along the beam. Okay, so here you have highly concentrated deformation energy in the central part. Remark that this scale is 200, 200, and 200, if I read well. So they are more or less the same scale in energy. So there is a different localization of deformation energy in different. So we are in the team of this meeting. Okay, and the snap through here. Look, you have straight lines here, and then these angles become negative. Okay, and so this is the difference between this branch, and this branch has a big stiffening. Okay.
Did you check if this is reversible?
Numerically, you mean? No, I don't know what it means, because, you know, the code of Emilio calculates the equilibrium, okay, then finds the residuals, and the residuals are very small, 10 to the minus something, and then he calculates the second derivative matrix, and it is definitely positive. So we could find other equilibria using different paths. But these are for sure equilibrium, stable.
Means that you don't use the previous equilibrium.
Yeah, but close. You look around one equilibrium, you choose another equilibrium which is relative to the displacement, in this case, changed a little bit. So in order to calculate the next equilibrium, you vary the displacement a little bit, and you start from the previously calculated equilibrium. So if your question is, are you sure that these are all the equilibria? No.
My question is, if you are increasing the displacement, what's happening if you decrease it?
I think you will get the same results unless we have lost some equilibria. So when coming back, you could decide to explore another branch. We can try it. For sure. Okay, but okay, these are the distribution of energy. I must go to conclusions. Okay, I was asking to Emilio to get the resultant reactions, the reactions as a function of displacement. And we get, this jump. By the way, there is a slide about energy, if I find it. Look here. When you have the small jump, the blue is extensional deformation energy, and the red is bending energy. So here you can relate the jump you have seen in the picture to the fact that suddenly elongation energy becomes lower and bending energy becomes bigger. So you activate another way of deforming this structure. Okay. So these are the reactions, and so you find that with the same force here, you have different reactions here. Okay, so this is another interesting stuff. Okay, so as you are interested in the plot, doing that, maybe we should show you later these plots, because we discussed them with Nicola Rizzi, but the plot was force displacement, right? When Nicola arrived at the point and he conjectured that this jump is related to a lost branch which is unstable. Okay, so we will try. I wanted to tell you what we have done yesterday, so the presentation is not perfect, but I prefer. Anyway, if anybody wants to help us in doing this, we are totally open to collaboration with everybody, including bad people. In the past, we found very bad people who collaborated with us for a while. Then when they found it is not convenient, they stopped doing the collaboration.
So, Francesco, the question was that if it's a snapback, that's interesting, but we are
Sorry?
If it's a snapback like that,
yes,
that's interesting, but we understand. If it's not a snapback, it's even more interesting.
I know.
Just the point.
But be sure that we tried to get the most interesting, and we could not find, but we will be more careful.
You have also the example of when you circle shell.
Yes.
When you press it like this, when you have the change of curvature.
Yes.
It's the same kind of phenomena.
Yes, but we went to the simplest case, which is for Mrs. Snap. This is the prototype of the simplest snap, I think. Okay, now I want to tell you that we can change. By the way, all these presentations, all the simulation were with extensional stiffness, and then bending stiffness and shear stiffness, given by these values. Something which I did not tell you is that with an analysis of rescaling, we discovered that in order to have second gradient continuum limit of this discrete system, you need that shear stiffness must be very small compared with the other stiffnesses. Otherwise, the system becomes a first gradient continuum. Okay, so in order to have exotic behavior, the shear stiffness has to be very low. So we are using this C very small. Okay. Now you vary elongation stiffness between 400, 4,000, 8,000, 12, 16, and 40,000. Okay? And you get this very different change of behavior. Here you have no snap through, you have here you have it bigger, and I suspect that here, and there we are in this region. So the snap through is not happening. Now what happens here, maybe Emilio can tell you better, but look, you have that these 2 points have as stiffness, rotational stiffness C, which is very small, while the central point has a bending stiffness B. Because when the pantograph becomes straight, you have one stiff rotational spring, one weak rotational spring, one stiff rotational spring, one weak rotational spring in the same line. So here the deformation energy prefers to have straight line here and there. And I don't remember, Emilio, this is definite positive or not?
This is a critical region. In this part of the graph, there are some, during the iteration, there are some cases with a stiffness matrix definitely negative.
Okay, so here you lose stability of equilibrium. Okay? But you told me that there is only one negative eigen direction.
One negative eigenvalue and the corresponding eigenvalue.
If I remember well, there is a criterion that we can use from the implicit theory where we are at the point, and if we have a tab root, that means that we have that the bifurcation diagram is like this, not a mess.
Okay. Rick's explained is a method which does not explore the singularities, but it's very simple to understand when we reach a singularity point, because looking at the composition of the stiffness matrix, there is one or more than one component on the diagonal which are negatives. In this case, we start with the eigenvalue analysis. In the previous, in this part, I remember that until this point, the stiffness matrix is definitely positive. From the last point of this curve and in this one, there are in some iteration the stiffness matrix becomes negative.
Not in all.
No, not in all.
Okay, so we need to discuss about this. Okay, and then I conclude with this. Okay, Emilio, please help me. Here the displacements are all the same and the scale is different, or these plots have different displacement?
Deformation is related to the last point of the equilibrium curve.
Ah, okay. So this is here,
yes.
This is here,
yes.
There, and there.
Yes.
Okay. Okay. Now, remark that, in a sense, we can prove numerically that when C increases, the behavior of this becomes less exotic. Because when C is big enough, you have a nonlinear beam, maybe with different equations, but a nonlinear beam. Instead, when C is small enough, you get softening, and you get this small inversion there. Okay? So please, let us keep discussing about this, because I think that we can do experiments about these things. We are already doing some experiments. So we can try to understand what is happening and find clever... okay, I will give you only a comment. I hope that playing with parameters, you can impose a kind of phase transition in these beams. So, with some displacements and some parameters, it is a Euler beam, and when you change displacement and parameters, parts of this beam is pantographic beam. So we could try to exploit this trick. Okay, so I think I've spoken even too much. I thank very much everybody.
Do you have some samples here?
We have some samples. Emilio Barchesi will show you on Friday. Okay. Okay, so there were many questions. You have some extra questions, or you want to? What is forecast after, Sam?
It's a turn of Johannes.
Okay, Johannes.
Granular materials.
Okay, please go. Let's go.